Hello, this is Lee Jun Hyuk from New Beginnings. Last time I explained UART, and this time I will explain I2C. For reference, there are UART, I2C, and SPI, and among these I personally prefer I2C. In my case, when developing hardware, I often work on projects where I need to connect and control multiple sensors to a single MCU. Using I2C makes it very simple to control multiple sensors. With UART, typical MCUs usually have only one or two instances available internally, which limits the ability to connect multiple sensors using UART. As for SPI, while it can also connect multiple sensors in parallel like I2C, it has its own constraints. I will explain SPI in more detail later, but to briefly touch on it, SPI requires a slave select pin, also known as a chip select pin, to communicate with a specific slave. This pin needs to be assigned to a GPIO. Since you need as many slave select pins as the number of sensors you are using, you are limited by the number of GPIOs available on the MCU. On the other hand, I2C only requires 4 pins: SCL, SDA, ground, and power, VCC. I will explain these 4 pins in more detail shortly. But with just these 4 pins, you can connect almost without limitation. Of course, with I2C, the maximum number of connections is 7 bits, which means 128 in the power of 2, excluding 0. You can connect up to 127 devices as slaves. Of course, in my experience, I have rarely connected that many. Generally, I have typically connected up to about 4 or 5 devices. I often compare I2C and some SPI. In my opinion, if speed is a critical factor, then SPI is the way to go. However, if speed is not as crucial, and for general use, I2C is commonly used. The reason it's important is that SPI has no speed limitations. Therefore, for high-speed requirements, like LCDs or other displays, SPI is often used. For control, in the case of I2C, according to the current specifications, the maximum clock speed can go up to 1 MHz, but in practice, I have rarely used it at that speed. This is because the slave devices also need to be compatible with specific speeds. For the sensors and IMUs I have used, they typically operate at 100 kHz or 400 kHz. So you can think of I2C as communicating at clock speeds of 100 kHz or 400 kHz. Let me explain in more detail while looking at a diagram of an I2C connection. If you look at the I2C diagram, it is structured like this. There is a master and a slave. There are pins such as VDD, power pin, SDA, and SCL. Although not shown here, you should also connect the ground. Similarly, the logic levels of the master and slave must be the same. 3V with 3V, 5V with 5V. Of course, some specific slaves have internal level converters that match the voltage, so even if the actual operating voltage is different, they will adjust the communication voltage accordingly. Anyway, the logic level communication voltage must be the same. To understand how I2C communicates, think of a metronome used in music schools. A metronome helps a musician maintain a specific tempo. Similarly, the SCL clock pin sends signals at a specific frequency, like 100 kHz or 400 kHz, to synchronize data transmission. The data is sent through the SDA pin according to this clock signal. Now there is a master and a slave. The master is the MCU, such as an Arduino, that we control. How does the master select and control a slave? I will explain this very simply. When sending data from the data pin, the first byte contains the address information. This address information is used to select the slave you want to communicate with. If there are multiple slaves with the same address, communication conflicts can occur. Therefore, each slave's I2C address must be unique. If you encounter issues while using I2C, consider these 4 main points. First, check the wiring to ensure the power, SDA, SCL, and ground are properly connected. Second, verify that the logic levels and communication voltages are the same. 3V with 3V, 5V with 5V. As mentioned earlier, if there is an internal level converter, this is a separate issue. Third, check the address. The master communicates with a specific slave using its address, so ensure the slave address is correctly input. Some slaves allow you to change their address by shorting specific pins, so make sure the address matches the one you intend to connect to. If communication still fails, it becomes more complicated. In such cases, use a logic analyzer, a tool often used for debugging UART or SPI, to analyze whether the clock and data signals are being transmitted correctly. This should help resolve most I2C issues. In this session, I have briefly explained I2C. In another video, I will explain SPI. See you next time.